Hey naturalist, Mrs. Mills here, and we are once again going to be live from my closet. For those of you who watched the last video, you may not believe me, but yes, I film or would now be filming our classroom videos in my closet. So I'm going to take you in so you get a kind of behind the scenes feel for what it's like to try to make a video when you're not good at it or lack technology, so you can kind of see. I think it's kind of funny. So there's my laptop, which turned off, and this is my new and fabulous design. I've made this to hold my phone as I videotape our class. So I'm shutting the door. So here we are. I think, can I flip this as I record? No, I don't think so. All right, so here's part 2 of modern genetics. So where we left off earlier, we were talking about selective breeding and genetic engineering. So I wanted to talk also about, just to wrap up this unit, about a really cool topic called cloning. Yes, so let's just chit-chat a little bit about cloning. Actually, it's just me talking. We could pretend that we're chit-chatting. But a clone is typically a genetically identical copy of an organism. It may be naturally occurring or created in a lab. So some things to think about. What if someone told you that they could clone you tomorrow? So typically when we're in the classroom, we'll pick a student and say, hey, who wants to be cloned today? Or I'll say, if you had a clone, what would you have your clone doing today if we told you we were cloning you? What do you think your clone would be doing? Now, typically my students would say, oh, I'd send my clone to school, or I'd make my clone do my homework, or I would be home sleeping or at the beach and my clone would be mowing the lawn. And that's a common misconception with middle schoolers. So we're going to go through, the process of cloning, how it happens, and what your clone would really be doing. We should be going to the next slide. There we go. Is this. So if we cloned you today, in 40 weeks or 9 months, your clone would be born. So you would have to wait for your clone to be made. It's important to know that when we clone something, whether it be an animal or a plant, it's not just a photocopy. It's not just an exact replica that's produced at that moment. Your clone isn't going to be wearing the same clothes as you, and your clone at that moment isn't going to be having the same thoughts as you. So if we cloned you today, you wouldn't be born, or your clone wouldn't be born, for another 40 weeks. Now, your clone, if this were you, would be genetically identical to you. So it should have the exact same DNA. And these exist, again, naturally in nature. And I'm wondering if you can think of 2 humans, sometimes 3 humans, that are genetically identical. Can you think of that? An example of that would be identical twins. So let's go through the process. This is the same diagram that I would typically give you in class. So typically, if we were to clone something, there are 3 organisms involved. Now, currently, we are not cloning humans, but I think it's easier if we introduce the topic using humans. So up here on the left, we have Fred. Now, Fred has a whole lot of money, and he thinks he's super fancy, and he wants to have himself cloned. So what Fred does is he will remove a skin cell. It could be from his elbow, from his knee, from his belly button. But a body cell, like a skin cell, contains all 46 chromosomes, or sets of DNA, right, that are unique to Fred, that are coded to make Fred. It makes Fred Fred. We take that body cell with all 46 chromosomes, and we actually remove all 46 chromosomes. We take them out of the nucleus. Here we have a lovely young lady, and she has donated an egg. Now, her egg would have 23 chromosomes because it's a sex cell. Half of her DNA is in that egg. But we don't need any of her DNA because we're going to get all the DNA from our friend Fred. So if we go back to her, what we have to do from our egg donor is empty the egg. We must remove their 23 of her chromosomes because they are not needed. And what we end up with is an empty egg cell. If we fill the empty egg with the 46 chromosomes from Fred, we end up with an egg cell that has all 46 chromosomes needed to make a new organism. But what's different than standard reproduction, I guess, is that all 46 chromosomes came from just one human. Now, we just have one cell with all 46 chromosomes. So we stimulate that cell to undergo mitosis, which is cell division, and you end up with a ball of cells. And that ball of cells needs to be implanted into our next character. It's a surrogate mother. So let's say Sally is our surrogate mother. If we implant this ball of cells that all have DNA, every single cell from Fred, into her uterus, trick her body into believing it is truly pregnant, she will grow and develop that ball of cells into a human, like she normally would. And about 40 weeks later, from the beginning, she will give birth to a baby boy that is genetically identical to Fred. Now, does this baby have any of the DNA or any similarities to its surrogate mother? No. Does this baby have DNA that's similar to that of the egg donor? No. All 46 chromosomes came from Fred. So this baby is Fred's clone. So you could see, if we look back at this image, that if we were to clone you today, you could not have your clone go to school for you because you would always be about 12 to 13 years older than your clone. I wonder what Fred would think about that. Now, again, we are not currently cloning humans for a variety of reasons. Now, my senior year of high school in 97, the world found out that they had cloned the first mammal. Now, this was really big news because humans are mammals. And they had been for a while cloning other types of organisms like salamanders and more simple organisms. This was the first time scientists had successfully cloned a mammal, and this was big news. So let's take a look once again at the process of cloning. We'll take a look at Dolly, since this is a true story. So here we have a sheep, and she had an udder, right? Because she was a female, and they removed, once again, a body cell from her. Now, a body cell is any cell from the body that's not a sex cell. So we're not talking sperm and egg. We're talking a body cell, could be from her cheek, from her udder, from her hoof, that has all of the DNA necessary to produce her. So that's her donor cell. Then we take here, okay, an unfertilized egg, so a sex cell from a different female sheep. And if you'll notice here, what we're doing is we're emptying the egg. They are removing the DNA, half the DNA that was needed to make this sheep. It has been removed. And you guessed it, what happens now is we take the DNA from the body cell, from the first sheep, and fuse it or fill the empty egg with it. And you can see that happening here. So now we have an egg filled with all the chromosomes from just one sheep. Again, you could see one cell becomes many cells over here through the process of mitosis. Once we have a ball of cells, it's called an embryo. It is implanted in the uterus of the surrogate sheep. Maybe we can call her Sally. And after the gestation period, or the amount of time it takes to grow that baby sheep, Dolly is born. And this is actually a real picture of what Dolly looked like. Now, Dolly ended up dying fairly young. She developed arthritis and a couple of other diseases as a result, and possibly of using, cloning or DNA from a body cell that might have aged more quickly. They're not really sure. But it's important to know that this wasn't just one trial. This was many years of research and thousands of trials that did not work. And this was the first time it happened. And it's a pretty amazing feat. So what I'd like to show you here was a really cool website. It was called Click and Clone. If you went to Google and typed in Click and Clone Mimi the Mouse, it was an assignment that I was going to have you guys do on your own. I was unable to do that because for some reason my Mac won't let me. So I can't give it to you as an assignment because I don't know if you can do it either. But it's super cool, and the sound effects are really cute. So again, it walks you through the process, and you get to go through it, of cloning Mimi the mouse. So I found the video on YouTube that we're going to watch. So you're watching a video on YouTube of this virtual lab that I wished we could have done together in class. So I'm going to pause this and just show you the characters again in the story. So we have Mimi. She's the mouse that we want to clone. Get it? Mimi. Want to clone me? Do you get two of me? Mimi. Megdo is the egg donor. And this is Mommy. Mommy is the surrogate mother. Get it? Like the mom. Kind of cute. And those are all the tools that you're going to use. And again, I'm going to encourage that you try this on your own. Considering I only have about 5 minutes left of recording. We might not make it to the end, but it's super cool for at least me to get a chance to show this to you as best I can. So they go through the steps. You could read all those. All right. So the first thing that you're going to have to do is take the body cell from Mimi and put it in here. They call that a somatic cell. And this is Megdo, the egg donor. You're going to remove her egg and put it in the Petri dish. So let's see if they do that for you. So you see the body cell. Then we're going to put both cells under the microscope. Again, this is a simplified version. So the first thing we're doing is removing the contents of the nucleus. So we're emptying the egg from the egg donor, from Megdo. So we have an empty egg. Next up is we need to fill that empty egg with the DNA from Mimi's, the mouse we're trying to clone, with her DNA. So you can see us removing the nucleus from the body cell of the mouse, Mimi, and then filling the egg right there with all of the DNA. So it's a complete set of DNA. And it's cute that they give us a little egg timer. They give you some information. I would encourage you to read all this. All right. Proceed to next step. So the next thing they're going to do is they're using a chemical called Divide-A-Lot. So again, we're stimulating cell division. So one cell needs to divide multiple times using a process known as mitosis until we have an embryo, which is a ball of cells that we can implant into the uterus or the womb of the surrogate mother, which was, I believe, Mimi. So you can see mitosis going on here. Now we have many more cells. Cells are dividing using mitosis. Egg timer says we're good to go. Awesome. Maybe you can guess the next step would be to implant that embryo, the ball of cells, into the womb, also known as the uterus of the surrogate mother. Now, the gestation period for mice is much shorter, so we're not waiting 40 weeks. It's about 19 days, and Mommy is able to give birth. And you can imagine that the resulting offspring, oops, I wanted to rewind that. Get back here, you. Here we go, and I'll pause it. Here, you might say, okay, so the offspring that resulted, is it going to look like Mimi, the mouse that donated the body cell and the DNA? Is this mouse going to be black, like Megdo, who donated her empty egg? Or is this mouse going to be light gray, like the incubator or the surrogate mother called Mommy? And you might know the answer. Let's keep watching. So, yes, it should be brown to match Mimi. And again, this goes into a little more detail about how organisms are cloned. All right. So again, I'm going to encourage you to go to Google and check this out on your own. The sound effects are pretty cool. And definitely worth a try. All right. So I'm just going to flip this around and we're going to leave the closet. See, I'm still in here. And I'm hoping that you found today's lesson useful, helpful, and easy to follow. And I hope everyone's doing well and getting outside as much as you can. We miss you. Mrs. Lupo and I, Mr. Mills and I really do miss being in the classroom. And we look forward to seeing you guys again soon.